Hello and welcome to Diplomatic Derivatives. In this series of lecture, we're talking about pure mathematics, where we are dealing with group theory. I have already uploaded a lot of videos about the basic concepts of group theory, including subgroups, cosets, Lagrange's theorem, permutation and symmetric groups, and a lot of other basic theorems as well as example questions. So make sure you check those out. The link is in the description box or the I button above. Those concepts are very important for basic understanding of the group theory, and I have also tackled with some examples from the past papers. So check those videos out before we move forward. Now we are going to talk about normal subgroups, and the theorems related to normal subgroups are very important from exam point of view. There are questions in the past paper of CSS related to normal subgroups. So let's see what is a normal subgroup and the types of normal subgroups, including certain theorems. Now, for any group G, if for the subgroup H, so what we're doing is we take a group and we take a subgroup for that group. Okay, left coset has to be equal to the right coset. Now the concept of cosets is the basis of normal subgroup, which you need to be thorough with first. Now what why do we need cosets here? Because with the help of the cosets we will be proving that certain subgroup is a normal subgroup. Okay, so the condition is that the left coset must be equal to the right coset. All right, then we can say that the subgroup is a normal subgroup of G. So if G is a billion, then H is definitely the normal subgroup. What does this mean? By abelian we know that the group has to be commutative. If the group is commutative, then we call it abelian, right? If the group is commutative, then all the subgroups of that group, we naturally say that they are normal subgroups. Okay, but in case when the group is non-abelian, then we cannot directly state that the subgroups are normal subgroups. In that case, you have to check the condition for normal subgroup, which we already stated here. We rearrange it. So how do we do that? You take one element of one element of G, let's suppose X element of G, and small h element of H. You take one element from the group and you take one element from the subgroup. To prove that that subgroup is a normal subgroup of G, you take the condition. You take one element from the left coset, that is XH, one element from the right coset, which is HX. You take those two elements. When those two elements become equal, that is, you are proving that both the cosets have same elements. That means XH is equal to HX. If you take this X on the other side, it becomes XH X inverse, right? Which will be equal to H according to this equation, right? Now this H, we know that it's element of capital H. So this means that this element XH X inverse has to be element of capital H. If this condition is true, so make sure you remember this. It's a very important condition, that XH X inverse, this element that you get, has to be present in the subgroup. Okay, so let's suppose in simple terms you can say that if A is element of G and B is element of H, then A inverse has to be element of H. Okay, this is what we basically mean when we talk about subgroups. For subgroups you have to check, you have a subgroup test, right? If A is element of G and B is element of H, then AB inverse has to be element of H. If this is true, then then H will be known as the subgroup of G, right? So similarly, for normal subgroups, this is the condition. XH X inverse has to be element of H. Okay, now this is a generalized statement that if H is the normal subgroup of G, if and only if XH X inverse is a subset of H. What does this mean? When we write capital H, it means that we are talking about a group. Okay, so this is we're talking about a subgroup. So this subgroup is included in the main subgroup. All right, this is a subset, right? So this is the subset of this. This means that H is a normal subgroup of G. This we get from where? When XH X inverse is element of H. We will do theorem, so it will be made clear. Now, before moving on to the theorems and other definitions, we'll talk about an example to make things clear. Let's suppose G is equal to 1, minus 1 iota and minus iota, and the operation here is multiplication. It's a group, okay? We take a subgroup. Let's suppose it is 1 minus 1, and since it's a subgroup of G, so the operation is same, multiplication. Now, for proving that H is a normal subgroup of G, what do we have to do? We have to take the cosets, okay? Through the basic definition that left coset has to be equal to the right coset. So how do you get the coset? From the cosets video, we have explained this, how to get cosets. I will just do a quick revision here. So in order to explain normal subgroups. Now let's suppose we take iota, right? One element from G and multiply from the its multiplication, okay? That's why we multiply from the left with all the elements of H, so you get the left coset, and when you multiply iota with the subgroup from the right, you get the right coset, okay? We have to prove that both the cosets are same. Both the cosets are same, then H is a normal subgroup of G, okay? We already know that this is a normal subgroup. This is a abelian group, and we know that for abelian groups all subgroups are normal subgroups, right? But in exam, obviously you get questions, you have to prove it, right? So how do you do that? The thing I just explained, you take one element of G. Let's suppose we take iota, you multiply from the left, you get iota and minus zero. You multiply from the right, again you get iota and minus zero. Since iota H is equal to H iota, therefore H is a normal subgroup of G, okay? Now, important definitions here: proper and improper normal subgroups. When we talk about improper normal subgroups, G itself is an improper normal subgroup of G, and a subgroup containing only identity is also an improper normal subgroup of G. All the other subgroups are known as proper normal subgroups, okay, except G and identity. If any group has more subgroups, all those will be proper normal subgroups if they are normal subgroups, okay? Now, what is a simple group? A group having no proper normal subgroups is called a simple group. Example, a group of prime order. That is a group which has only which has only improper normal subgroups. That is, it has only G and identity, right, as the subgroups. So that group will be known as a simple group. It has no proper normal sub. It does not have this part, okay? Example we are given is a group of prime order. Let's suppose the order of a group is 7, right? It will not be having any proper normal subgroup, okay? How do we this thing, a group of prime order, we can also prove it with the help of Lagrange's theorem. Now, what does the Lagrange's theorem say? Lagrange's theorem says that, we did a video for this as well, and we can prove with this example that any subgroup, the order of a subgroup divides the order of the group, okay? In that case, we can say that it's a subgroup of G, okay? So for any group to be known as a subgroup, it means that the order of the subgroup will divide the order of the group, right? So in this case, in group of prime order, we cannot say that, because what is the order of this main group? It's, let's suppose it's 7, right? Now there won't be any number which can divide 7, because 7 is a prime number, right? It does not go in any other table, right? Therefore, we cannot get any subgroup of any order which will divide 7. So we won't have any subgroups. Since there are no subgroups, so there cannot be any proper normal subgroup, right? So that group will be known as a simple group. Now, another definition is Hamiltonian group. This can come in MCQs. If all subgroups of a non-abelian group are normal, then the group is called Hamiltonian group. We said that if a group is abelian, all the subgroups are normal subgroups. If the group is non-abelian, in that case you have to check the condition, right? Upon checking the condition for all the subgroups, if all of them turn out to be normal, then that group will be known as the Hamiltonian group. All right, now we take the theorem. Every subgroup of an abelian group is a normal subgroup. This is the first condition that we talked about. Every subgroup of an abelian group, we said that they are naturally, all those subgroups will be normal subgroups. So now we prove that. So what you take one subgroup, let's suppose it's H, and you take an abelian group, let's suppose that's G, right? Now, X element of G and H element of H, right? Then to prove that it's a normal subgroup, what you need to do? You have to use the condition that you have to prove that X inverse is also element of H. This is what you have to prove. So you take that X inverse, right? And with that, what do you do? XH can be written as HX since G is commutative, right? Now, since it's the group, so it's also associative, right? So if it's associative, then X and X inverse can be written together, right? This X and X inverse will become identity, right? So HE will be equal to H, and this H is element of capital H. Therefore, this thing that we took in the beginning is also element of capital H, right? This is what we have to prove, that if X is element of G and H is element of H, then this thing is also element of H. So we just proved that. Therefore, H is a normal subgroup of G. So X element of capital G, H element of H implies X inverse is also element of H. So H is the normal subgroup of G. Simple. Next is a subgroup H of a group G is normal subgroup of G if and only if, that is, you will be doing converse as well. H normal subgroup of G if and only if X inverse is equal to H. This is one part of one of the past papers as well. So we will see how do we solve this. First, you take the first side. You will assume that H is a normal subgroup of G. By assuming this, you will reach this conclusion. Then in converse, you will take this side and you will reach this. Okay. So we start with taking, let's suppose H is a normal subgroup of G. Since we are already saying that H is a normal subgroup of G, then by definition, we know that X inverse will be a part of capital H, right? This is by definition of a normal subgroup. Since this thing is element of capital H, it means what? That a set which contains, means a group which contains this element is what? This, in place of small h, you can write capital H, right? It becomes a group, right? Now this will be a subset of capital H because since this belongs to capital H, right? So this group will also belong to capital H, right? This is the first condition. Let's suppose this is first statement. Okay. Again, now X element of G, and we just prove that X inverse is all a subset of H. What do? Now you take the inverse of this thing, because since we're talking in groups, a group has inverse, right? You take inverse of this. So in place of X, you can write X inverse. H remains as it is, and X inverse becomes X inverse inverse, right? Now this X inverse becomes X, right? So you can write X inverse H. X is a subset of H. Okay. Now what you do? You take X and X inverse on both sides. So this X inverse becomes E, and this X inverse becomes E. So you're left with H on this side and X inverse on the other side. Let's suppose this is statement number 2. Now from 1 and 2, what do you understand? You take the first statement, X inverse subset of H, and the second statement, H subset of X inverse. If this belongs inside this and this belongs inside this, then both are equal, right? So from statement 1 and statement 2, you get X inverse equals to H, right? It's clear, right? From the first statement, if this belongs to this and this belongs to this, means these two are equal, right? This means that if this is the condition that we took, then H is a normal subgroup of G, and what did we get? We get X inverse equal to H. This is what we have to prove, right? Therefore, if H is a normal subgroup of G, then X inverse is equal to H. Okay, one mistake here. Instead of writing this sign, okay, use only one-sided, because this is what we proved till now. Okay, we proved this side. Now we are going to prove the opposite side. Okay, we're going to take this statement and we prove this. So we take X inverse is equal to H. Okay, now since this is equal to H, it means that this is a subset of H. Now from this, what is the element inside this set? The element inside this will be, instead of capital H, you can write small h, right? It means this thing is element of capital If since this is a subset of H, it means all the elements inside this belong to this, right? So this element obviously belongs to H then, right? So this is the condition of a normal subgroup, that X inverse element of H. Therefore H is a normal subgroup of G. Okay, so now you can write both side double-sided arrows, that is H normal subgroup of G if and only if X inverse is equal to H. Okay, so we took one side, we proved the second one, we took the second side, we proved the first one. All right, this is what we are trying to prove here. So that's all for this video. I hope you were able to understand the concept of normal subgroups and the theorem that I explained related to normal subgroups. Now in the next video we're going to talk about more theorems on normal subgroups that are also very important, can come in exam, and also part of one of the past papers as well. So stay tuned for that video. Before moving on, make sure to like, share and subscribe to my channel. That's all for today. Take care. Bye bye.